Hello, everyone. This is Mohamed speaking, and today I'm going to present my thesis under the topic of water quality monitoring and mapping using rapidly deployable sensor nodes. So, in the beginning, I'm going to start presenting the outline of our presentation. I'm going to start with a brief overview, and then I'm going to explain the method that we're using in our study. And then I'm going to go deeply into the system hardware, and then I'm going to explain the fundamentals of kriging, and then we're going to explain the validation of our system, and then finally the results and discussions. Overview. We all know that water covers 70% of planet Earth, and clean water is fundamental human right and a critical factor in public health, agriculture, and ecosystem. However, the quality of our water resources is under constant threat due to various pollutants, industrial activities, and climate change. That's why it's really important to have a continuous water quality monitoring to ensure the safety and sustainability of our water resources. However, performing continuous water quality monitoring using the traditional methods can be challenging for many reasons. For example, it's going to be labor intensive, high costs. We're going to have like access to limited data, delays in data reporting, spatial variability, and incomplete monitoring. That's why it's important to have an advancing testing method. And for example, it should be automated real-time data collection, multi-parameter monitoring, data processing and interpolation, and long deployment duration. The method in our study depends on a UAV designed by Art's lab team. This UAV is going to carry out our sensor package and deploy it in the desired testing pond or the water body that we want to test. The deployment mechanism is going to be based on electropermanent magnet, which use electric current to create a magnetic field. And this current controls the magnetic field and can be toggled on and off. After collecting our data from the sensor package, we're going to employ kriging to create a spatial representation of the water parameters on a map. And this will help us to identify the areas of concerns and assess the overall water quality. Our in-situ water quality sensor package, it's a real-time multi-parameter monitoring. It's capable to store data on site. It's an aerial deployment, power efficient, long-term testing capability, floating capability, and it's fully waterproofed. Our sensor package consists of two parts, inner part and outer part. The inner part consists of a tray, which is holding all the electronic components inside it. And the electronic components consist of a battery, PCB, microcontroller, and sensor modules. The outer part is acting as a housing for the inner part and consists of sealing cap, buoys, metal grip, and this is the part which is going to be attached to the UAV, and a probe protection cap. The following flow chart is showing the sensor package data collection algorithm. It's going to start by initializing the Arduino, and then it's going to check for the initialization of the SD card. If no, it's going to ask for checking the connections. If yes, it's going to initialize the RTC and then initializing the sensors. After that, there's going to be a delay time, depends on the sampling time that we had adjusted. And then it's going to start collecting the data from the sensors. After that, it's going to read the current time from the RTC, and it's going to save both the data and the time on the SD card. Our sensor package consists of 4 main sensors: pH, TDS, which is the total dissolved solids, turbidity, and temperature. The reasons for choosing those sensors: the pH is for measuring the acidity and alkalinity of the water. TDS is measuring the dissolved substance in water, and the high level of the minerals inside the water can affect the irrigation process. Turbidity indicates the water cloudiness, and this can be a sign of contamination inside the water. Temperature, of course, it's for measuring the temperature of the water, and this is going to be related to the solubility of oxygen inside the water. system hardware. We got 4 sensor modules in our sensor package. We got 4 main sensors in our sensor package: pH sensor, TDS, turbidity, and temperature. All our sensor modules are analog sensors, except the temperature. It's a digital sensor. All our sensor modules operating voltage is 5 volt, and the range for the pH is the unit range for the pH is from 0 to 14, and the TDS is from 0 to 1000 part per million. The range for the turbidity sensor is from 0 to 100 nanometric unit. The temperature ranges from -55 to 125 Celsius. The data logger consists of 3 main components: the RTC, the micro SD card, and an LED. The RTC that we have used surface mount IC and includes a coin cell battery backup, and it's known for its compact size. And for the SD card, the operating voltage is 3.3 volt, and it's also known for its compact size. The LED is acting as an indicator while saving the data on the SD card. The microcontroller that we use in our sensor package is an Arduino Nano. It's known for its compact size and low cost. Then we start designing a schematic which include all the electronic components for our sensor package to ensure the effective operating procedure and for error prevention. After designing the schematic, we start designing a compact PCB, which is going to include all the electronic components because we have a limited space. And as you can see, the size of the PCB was very small. It's 97 millimeter in length and 32 millimeter in width. The powering source of our sensor package is a rechargeable LiPo battery, 7.4 volt and 1000 milliamp hour. The current flow diagram is displaying the internal component of our sensor package. As you can see here, the LiPo battery is powering our microcontroller, and the microcontroller is powering the SD card and the RTC and the 4 sensor modules that we got. Kriging. Kriging is a geostatistical interpolation technique used to predict data at the unsampled location by considering the sample points and their spatial relations. Kriging depends on a semivariogram, and the semivariogram is a spatial relation map that illustrates how data points become more similar or different as their distance from each other changes. And it consists of 3 hyperparameters: the nugget, the range, and the cell. The nugget represents the variation of the data at very small distance. The range is the distance in which the data points are correlated, and beyond this range, the data points become uncorrelated. The cell is the total amount of variation in the data set. And here's an example to make it easier to understand it. We got 3 known points, and we're trying to predict point 0, which its color is green. So first, we're going to start by including all the elements inside matrix B, which is the distance between the known points. For example, H11 is going to be the distance from point 1 to itself, which is going to be 0. H1 to 2 is going to be the distance from point 1 to point 2, and so on. B node is going to be the distance from the point that we want to predict to the points that it's known, or our observation points. Once we finish our 2 matrices, we get the semivariogram equations. It's going to depend on the distance. So if your distance is 0, for example, like H11, we're going to use the first equation, which is going to be 0. And for the second equation, if the distance ranges between 0 and lower than your range or equal, we're going to use the second equation. The third equation is going to be used if your distance is more than the range. And C is presenting the cell, C naught is the nugget, and A is going to be the range. After plugging in our matrices in our equation, we're going to have V and V naught. These two matrices, we can use them to calculate the weight. And the weight is showing how important is the observation point to the point that we want to predict. So for example, if our observation point is close to the point that we want to predict, is gonna have a higher weight. To calculate our weights, is gonna be the inverse of matrix V multiplied by the matrix V naught. Z naught is presenting the point that we want to predict, and to calculate it, it's going to be the summation of the dot product of the weight and the observation points values. Validation. To ensure the validation of our kriging method, we generated a fake lake by using MATLAB, and this fake lake is simulating a distribution of pH values across its surface. After that, we start taking random points, and we employ kriging to see like how accurate is our prediction by using the kriging. And as you can see, first we start with 4 sample points, and then we increase it to 6, 8, and 10. After that, we increase it to 15, 20, 25, and 30. And as you can see, it's once we increase the sample points, our prediction became more accurate. And as you can see here from the plot, the relation between the error and the number of sample points are inversely proportional. So once we increased our sample points, we start having less error and more accurate prediction. Another test for validation is testing the deploying mechanism. So we used the flume in the civil department lab, and we used the UAV to carry out our sensor package. And then in the second picture, as you can see, it released the sensor package, and then the sensor package was submerged inside the water, and then it reached out to a floating position. Sensor validation. For validating our sensor package measurements, we used 3 industrial sensor, pH and TDS, and a K-type thermocouple. We found out that the absolute error for the pH was 1.34%. The TDS was a little bit higher, it was 5.23%, and the temperature was 0.81%. The results: we deployed our sensor package in a stationary pond on campus. We deployed our sensor package in 6 different locations. And then after collecting our data, we employed kriging. So as you can see here, we found out that the bottom left corner here, it has a higher pH values, and this is because of the presence of algae. And while testing the pond here, there was a concentration of sunlight, so we got a higher temperature, and this caused the higher TDS values. The left-hand side of the pond, it showed a high turbidity values. Another test was conducted. It was a power management test to see how long our sensor package is going to last. It lasts for 32 hours and 48 minutes. The last test we conducted, we wanted to test the capability of our sensor package to be deployed in a dynamic environment. So we deployed our sensor package in the creek behind 300 main, and we tied the sensor package with a steel rope into the bridge. And these are the results that we found from the test. And currently we're working on a journal paper, which is going to be submitted to the MDPI sensor, and the estimated submission time is going to be December 2023. At the end, I want to thank Dr. Downey for his guidance throughout my master's, and I want to thank Dr. Imran and Dr. Banerjee for attending today. Thank you.